Hey guys, today we're going to be looking at a specific type of solution stoichiometry problem where we are asked in the event of a precipitation reaction, so a reaction where a solid is formed, what would the concentration of every ion in the solution be after the reaction is complete? So we're going to need to use the skills we learned in the last couple of videos to do solution stoichiometry, and we're going to be connecting this now to limiting reactants from our Unit 1. How exciting is that? In order to get this done, we're going to go ahead and start by talking about some vocabulary you need to be aware of. We're going to do some practice problems. I'm going to show you a demo reaction. Now this demo reaction I call the glitter gold reaction or glitter gold lab. It's kind of fun and it shows a really great precipitation reaction that we're actually going to use in the course of a practice problem. I'm going to show you that math behind that reaction, and then I'm going to give you a chance to try this on your own. So let's go ahead and get started right off the bat. First thing you need to be aware of are a couple of words that I'm going to be using throughout the course of this video. First one is precipitate. Precipitate is the solid created over the course of a reaction. So essentially what we're doing is through the course of a reaction between two aqueous solutions, creating an insoluble product that falls out in the form of precipitate. Now we've used this word before, I just want to make sure you're aware of it. The second one we're going to talk about is the supernatant. Now the supernatant is the solution above the precipitate. So these are all of the ions that are not a part of the precipitate itself. This is one type of problem where you're really going to have to know how these things that we're looking at are soluble or insoluble. If you can predict solubility, you're much further ahead. Sometimes the problems will give you which one is the precipitate, but not always. You cannot assume that you will know which one is going to precipitate out or not. You might have to make a prediction yourself, and in that case you're going to have to use the solubility rules that we talked about earlier in this unit. So let's take a look at one of these reactions. Here I'm going to take lead nitrate and I'm going to combine it with potassium iodide. Now lead iodide is insoluble, so what I'm about to show you is a footage from this reaction. So let's go ahead and take a look. Now over this reaction, what's going to happen is the lead and the iodide are going to react together to form a bright yellow precipitate. When this precipitate forms, what's going to end up happening is it's going to stay in solution. I'm now going to go ahead and heat up the lead iodide solution and then cool it down very slowly in order for it to then form crystals. These crystals are exceptionally pretty. They're very glittery, so let's go ahead and take a look at this process. Here's an animation that's going to show you what is actually going on at the molecular level in the precipitation reaction that we just saw shown in front of you. Now what's going on is that molecules are moving randomly. When two iodide ions come into contact with a lead ion, they form a solid precipitate because they are insoluble. Meanwhile, the spectator ions in this situation, the ones that aren't involved in the precipitation reaction, continue to float around the solution, bumping into each other and the walls at random. Now we're going to do a practice problem where I'm going to show you how to find the concentration of ions after a reaction is complete. So here's the problem. We have 0.3 grams of lead-2 nitrate dissolved in 250 milliliters of water. We are going to add that to 0.5 grams of potassium iodide, which is also dissolved in 250 milliliters of water. So we combine those two solutions together. I want to find the concentration of every ion in the solution after the reaction is complete. Well, first we need to predict the reaction. So now we need to write a chemical equation regarding the reaction between lead-2 nitrate and potassium iodide. So let's go ahead and do that first. So here's our reaction. It's going to be a double replacement reaction where the lead and the potassium are going to swap places. So we form lead-2 iodide, PbI2, and potassium nitrate, KNO3. You'll notice this is not balanced. We need to go ahead and balance it. Easy way to balance in this case, because we have two iodides here. We need to make sure we have two here. Now we have two potassiums and two nitrates here, so we need two over here. So we're balanced. Once we've balanced, we can already identify one key component to this reaction. It's going to involve a net ionic equation. So let's identify the net ionic equation next. Now, lead nitrate is fully soluble because all nitrate salts are fully soluble. Potassium iodide is fully soluble because potassium is an alkali metal, therefore it's always going to be soluble. Lead iodide, well, this is one of those exceptions that we talked about in our solubility rules video. Iodide, although almost always soluble, is insoluble in the presence of lead, mercury, or silver ions. So here we've got lead, so it's going to be solid. This is our precipitate. And then we have potassium nitrate, which is always soluble. So we have lead iodide as our precipitate, which means that the lead and the iodide ions must be contributing to creating the lead iodide. So those are going to be in our net ionic equation. And there's our net ionic. Now here's the key to the net ionic equation. The net ionic equation is going to tell us only the ions involved in the reaction. But I asked for all of the ions. So what I'm going to do is I'm going to first, by identifying the spectators, find the concentrations of those. The spectators are the easiest to find in this situation because of the fact that the amount you add is the same as the amount that comes out. In other words, the total volume is going to change, but the number of moles of nitrate and the number of moles of potassium that you added to the actual reaction total didn't change. Same in the beginning as they are at the end because they're simply spectators. So what I'm going to do is I'm going to start by finding the concentrations of our spectator ions. Just as a heads up, brackets around each of these represents concentration in moles per liter. So when I show this notation, that's talking concentration. So we're going to start by finding the concentration of our two spectators here. Let's go ahead and do that. We're going to start with potassium. Now potassium came from our potassium iodide. We had 0.5 grams of it. We first need to find the number of moles of potassium added to the solution. So we're going to take our 0.5 grams divided by the molar mass of potassium iodide, which by the way is 166 grams per mole, and that'll give us the number of moles of potassium that we added to the reaction in the beginning. Because potassium in potassium iodide is a 1-to-1 ratio, we're going to end up just multiplying across the top, 0.5 times 1 times 1, dividing across the bottom, 166 and 1. And our total value is going to be 3 times 10 to the negative third moles. So that's the number of moles of potassium ions that were in the solution, but we need to divide by volume. Be careful here. Volume of the potassium iodide solution was 250 milliliters, but we performed a reaction where we combined two solutions together. And because we combined two solutions together, the volumes were additive. Our final volume is in fact 500 milliliters or 0.5 liters. So we're going to take this value, divide it by 0.5 liters. And we get a value of 6 times 10 to the negative third moles per liter or molar potassium ions. So there's our answer for the number of mole or the concentration of potassium ions. Nitrate's going to be handled the exact same way that we just handled the potassium. We're going to start by looking at how much nitrate was added through the stoichiometry, going from grams to moles, and then dividing by the total volume. So 0.3 grams of lead 2 nitrate was added to the solution. Now, be aware that lead 2 nitrate isn't quite as simple as the potassium iodide. Potassium iodide was a 1-to-1 ratio. Lead 2 nitrate, it's a 1-to-2 ratio. For every 1 mole of lead 2 nitrate, we actually have 2 moles of nitrate ions. So be careful with that. So let's do the stoichiometry, going from 0.3 grams of lead 2 nitrate to the number of moles of nitrate ions. Something to be aware of is the molar mass of the lead 2 nitrate is 331 grams per mole. So what we have here is a situation where we have 0.3 grams of lead 2 nitrate. We're going to do our conversion from grams to moles using our molar mass. We're then going to multiply by 2 because there's 2 moles of nitrate ions in every 1 mole of lead 2 nitrate. We end up getting a value of 1.81 times 10 to the negative third moles of nitrate ions. Now remember, the volumes in this situation are additive. So we have to make sure that we are dividing by the total volume of the solution, which is 0.5 liters. That's going to give us our final concentration of nitrate ions in our solution of 3.6 times 10 to the negative third moles per liter. Next, we're going to tackle the harder situations of the ions that are involved in the precipitate itself. For the next two that are involved in the actual precipitation reaction, so the lead ion and the iodide ion, we're going to have to handle this like a limiting reactant problem. We need to figure out how much of a product each reactant can produce. Well, might as well look for the lead iodide because that's the only product they're both going to be actually participating in creating. So we're going to start with the number of moles of lead ions. The way we do this is just like we do any other stoichiometric problem. Start with the number of grams, divide it by the molar mass, multiply by the mole ratio of lead ions in the lead 2 nitrate. That happens to be 1 to 1. So let's go ahead and do that using, again, the molar mass of lead 2 nitrate of 331 grams per mole. So with this, we know that we can create 9.06 times 10 to the negative fourth moles of our lead 2 iodide. Okay. Now, just so you're aware, it's 1 mole of PbNO3 It's actually going to be to 1 mole of PbI2 here. So that was a quick typo I made, but that's not a big deal. So the whole idea is that it's a 1-to-1 ratio here in our overall balanced equation. Now what we're going to do is we're going to do the same math, but we're going to do it with potassium iodide using the iodine ions. In this situation, if we look at our chemical reaction, we have 2 moles of Ki for every 1 mole of PbI2. So when we're doing our conversion here, our mole ratio is actually going to be 2 to 1. If we do out this math, what we realize is that we can create 1.51 times 10 to the negative third moles of PbI2. Well, what that means is that we can produce less moles of our product, PbI2 lead iodide, with our lead ions than we could with our iodide ions. That means lead 2 nitrate is our limiting reactant. Now, for today's purposes in this unit, we're going to assume that means it's all used up and that there's none remaining in solution. So we're going to make the assumption that our concentration of lead ions in solution is 0. Once we get to actual equilibrium type questions later in the year, we're going to learn that that's not necessarily true. And we're going to actually learn the true concentration of those lead ions later in the year. But for the moment, we'll assume it's 0. Now we need to figure out how much iodide was in excess. In order to do that, we take the amount of lead 2 iodide that we actually could create, here, 9.06 times 10 to the negative fourth, and we figure out how much iodine ions we needed to use to create that. So let's do that next. Now what we need to do is we need to look and see if we can make 9.06 times 10 to the negative fourth moles of our lead 2 iodide as a product. How much of the iodide ions were used to do that? What we're going to do is basic stoichiometry. Now, the nice thing is the lead 2 iodide, the mole ratio here is going to be 2 moles of iodide ions, I minus, to 1 mole of PbI2. So So that tells me that I had to use 1.81 times 10 to the negative third moles of iodide. So what I'm actually going to do is say moles of iodide used to give it a little more context. Now, if I can figure out how much iodide I started with, I can go and figure out how much I have left. The nice thing about the iodide is the fact that we created the iodide with, or we came from, the potassium iodide. So we're going to do the same math that we did earlier. I'm just going to do it again. You certainly don't have to because the math would or should be on your paper. But what I'm going to do is do the math again just to show you where we're coming from. 0.5 grams of potassium iodide. We're going to divide by the molar mass to figure out the number of moles of iodide that we started with. So we started with 3.01 times 10 to the negative third moles of iodide. So we started with this amount. We used that amount. The difference between the two, that represents how much of the iodide remains in solution. So we do this math out. 3.01 times 10 to the negative third minus 1.81 times 10 to the negative third, and we end up with 1.2 times 10 to the negative third moles of iodide remaining in solution. As we have previously, this is just the number of moles. We need concentration, so we divide by the total volume, which is 0.5 liters, 1.2 times 10 to the negative third divided by 0.5. That gives us our final answer of 2.4 times 10 to the negative third moles per liter of iodide ions. And there we've done it. We have now found the concentration of every ion remaining in solution, and we have assumed that our limiting reactant, in this case the lead ion, has gone to 0. Next, we're going to do one that you're going to try on your own and give you a chance to kind of test what we've just learned here. All right, now I want you to try this problem on your own. Take a few minutes, pause the video, work through the problem. If you get stuck or if you get an answer, go ahead and unpause the video and we'll work through it together. All right, now that you've had a couple of minutes to work through it, let's go ahead and work through it together. We have in this situation a problem very similar to the last one we went through. We have two solutions being added together. A reaction is going to happen. First of all, we need to figure out what that reaction is going to be. This requires us to write our chemical equation. We're going to have potassium sulfate combined with, in this case, barium nitrate, and we need to predict our product. So let's go ahead and do that first. So we predict that we would get potassium nitrate and barium sulfate. Now, remember that sulfate's -2, so therefore here it's -2 as well. Barium's +2, so barium's +2 as well. Now, what this means is that we're not balanced. We're going to have to balance the reaction next. And if you look, now we're balanced. 2 potassiums on the product side and 2 on the reactant side. 2 nitrates on the product side, 2 on the reactant side, 1 barium and 1 sulfate on each side as well. So we're balanced. The next thing we can do is identify what are our ions in the first place. We're going to write a net ionic equation. So let's go ahead and do that. First of all, potassium sulfate is going to be fully soluble, as is barium nitrate. Potassium nitrate fully soluble, but barium sulfate, there's a precipitate, all right, insoluble. So if we're going to cancel out our spectators, we can turn this into a full ionic equation and then cancel out our spectators. So we end up with a net ionic equation. Now what this means is that potassium and nitrate are our 2 spectators. Remember from the last problem, these are going to be the easiest to identify, and so we're going to start with those as we're looking at the concentrations of every ion left in solution. The reason the spectators are the easiest is because their concentrations don't change. The number of moles of these 2 ions that we added are the number of moles that we end up with. So here's what we're going to do. We're going to look at our spectators first, nitrate and potassium. So we're going to look at those two first, and then what we're going to do is we're going to take a look at the two ions involved in the precipitate. All right, so remember, the first thing we're going to do is look at the amount that we added. So let's go ahead and do that. All right, so starting with our spectator potassium ion, let's go ahead and start with the fact that we have 100 milliliters of 0.1 molar solution. So we need to figure out how many moles of potassium ions we have in the solution, because remember, that doesn't change because it's a spectator. So 0.1 moles of potassium sulfate for every 1 liter of potassium sulfate. Remember that we need to figure out moles of potassium ions. That's a 2-to-1 ratio. So 2 moles of potassium ions for every 1 mole of potassium sulfate. And what that tells us is that we have 0.02 moles of potassium ions. That's moles. We need to figure out concentration, which means we need to divide by volume. Be careful. Remember, we have to divide by the total volume at the end of the reaction. That means we added 100 milliliters to 100 milliliters. So our new volume is 200 milliliters, or 0.2 liters. So we're going to take this value and divide it by 0.2. Which means our concentration of potassium ion is 0.1 moles per liter. Let's do nitrate next. For nitrate, what we're going to do is we're going to do the exact same procedure where we're going to take our 100 milliliter solution of 0.2 molar barium nitrate, and we're going to figure out how many moles of nitrate we have in solution. Remember that in this case, nitrate is at a 2-to-1 ratio, so we need to multiply by 2 moles of nitrate for every 1 mole of barium nitrate. And this means that we end up with a total number of moles of 0.04 moles of nitrate out of the barium nitrate. So we have 0.04 moles of nitrate. We're going to divide that by the total volume, which again is 200 milliliters. So we're going to divide that by 0.2. And we end up with a final concentration of 0.2 moles per liter of nitrate ions. All right, so next we're going to look at our precipitate. For our precipitate-involved compounds, so these two ions, barium and sulfate, we need to handle it just like we would any other limiting reactant problem. Figure out how much of our product, in this case the precipitate, could each make. The one that makes the least precipitate would be our limiting reactant. The other one would be an excess. So let's find the limiting reactant. We're going to take the barium and the sulfate ions and figure out how much of the barium sulfate each one can make. So let's go ahead and do that now. For barium, our mole ratio is 1 mole of barium nitrate to 1 mole of barium sulfate. And this means that with the barium ion alone, we can produce 0.02 moles of barium sulfate. With the sulfate ion, we're also at a 1-to-1 ratio. Which means we can create 0.01 moles of barium sulfate. This tells us that our sulfate ion is limiting. Now, we are going to make the assumption in this unit that that means it has a concentration of 0. All right, remember, that's just an assumption. Later in the year, we're going to talk about why that's not always the case and why there might actually be some sulfate left. But for the moment, this is our assumption. That means we need to figure out how much barium is left. The way we're going to do this is we're going to figure out, well, how much barium sulfate was made in the first place, which, by the way, is this, 0.01 moles, and figure out how much of that barium was necessary to do it. And let me do that next. So we found that you can produce 0.01 moles of barium sulfate with our limiting ion, the sulfate ion. We need to figure out how much barium needed to be used to make that. Well, the way we do this is we simply do some quick stoichiometry. 0.01 moles of barium sulfate. One-to-one ratio between the number of moles of barium ions necessary to create the number of moles of barium sulfate ions, or sulfate formula units. So we have a 1-to-1 ratio, which means that we had to use 0.01 moles of barium ions. So that's how much barium ion was used to create our precipitate. Now we need to figure out how much we started with. Well, remember we started with 100 milliliters of 0.2 molar barium nitrate. Because it's at a 1-to-1 ratio, we start with 0.02 moles of barium ions. This means because we start with 0.02 moles of it and we use 0.01 moles of it, we have 0.01 moles of barium ions remaining. So if we have 0.01 moles of barium-2 plus remaining. That gets divided by our total volume, which is, in this case, 0.2. So 0.01 divided by 0.2 gets us to a concentration of 0.05 moles per liter. So here we have now found the concentrations of every ion left in solution at the end of our reaction. All right, so that wraps up today's video. Let's do a quick recap. Today we talked about how to solve for specific precipitate-related solution stoichiometry problems. Now, these are arguably the most common type of problem you're going to see in solution stoichiometry this year. Part of the reason is because we love to do data analysis using the amount of precipitate formed. In order to figure out the ions left in solution, we first need to figure out how much precipitate formed by looking at it as a limiting reactant solution stoichiometry problem. Then what we can do is, using that knowledge, we can figure out how much of ion was in excess and what are the concentrations of spectators. Be careful. Remember that all solutions that are added together, the volumes must be added together. Also, solids by added alone don't necessarily impact the volume, and oftentimes they'll tell you to assume that it doesn't. So be careful with added volumes, when you add volumes and when you don't. I'd like to thank Maddie Morgan and Christina Trudeau for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.